So hi, in this video we are going to learn about electric flux and Gauss law. In order to understand Gauss law, first basic requirement of understanding of electric flux is required. So what is electric flux? Electric flux electric flux is defined as number of field line, electric field line passing through a surface, and this surface can be open and closed. Open surface means like open surface like planar sheet. When electric field lines are passing through the sheet, it is called open surface. And closed surface like cube. If electric field lines are passing through a cube, it will be called as closed surface. Like this, if electric charge is inside it and electric field lines are passing through this, then it is called as closed surface. And sphere is also known as closed surface. So this is the basic thing about it, and let's talk about electric flux in more detail, how to calculate it. So electric flux calculation. So electric flux, so assume that these are the electric field lines, and there is a planar sheet inside these electric field. This is the planar sheet, and this planar sheet is made up of small area element dA, and this area element dA vector is perpendicular to this surface. So dA is in this direction, dA vector, and electric field is in this direction. So flux is defined as phi is equals to, if I talk about the small area element flux, so it will be d phi integration E vector dot dA vector, and this is dot product. So electric field and dA vector, so angle between them is like theta. So we can say that electric field and magnitude of electric field and dA cos of theta. So phi is defined as like this. So electric field is constant, and so it can be put outside the integration, and this will be dA cos of theta. So flux phi is defined like this. So this is the equation. To understand it better version, let's take another example. So these are the suppose electric field lines, and planar sheet is placed inside this like this. So dA vector will be along the electric field. dA is along the electric field. So electric field direction and dA direction is same. So angle between E vector and dA vector is 0. So like theta is equals to 0. Theta is equals to 0 degree. So flux d phi is defined as E vector dot dA vector. So E vector can be put outside because of the constant, and dA cos of theta, and theta is equals to 0. So E, simply flux phi will be E into area. So this is flux phi in this case. And what if electric field is in this direction like this? Electric field lines are like this. These are uniform electric field lines, and a planar sheet is placed like this. Planar sheet is placed like this, and dA, area element dA, will be perpendicular to this surface. It will be like this, dA vector, and electric field is in this direction. So angle between electric field and dA vector is theta is equals to 0. So d phi E dA cos, angle between them is 90 degree. So it is 90 degree. So electric field and dA vector is 90 degree. So this is cos 90. So E dA cos 90 is equals to 0. So flux phi in this case will be 0. No flux passing through this surface. Let's take one more example in which electric field lines are like this. And like a sheet is kept like this at angle of 60 degree. Assume this is 60 degree, and this is direction of electric field, and this is direction of dA. So flux phi, d phi, can be written as E vector dot dA vector cos 60 degree. So electric field is constant E, and the small area of element will give dA, integration will give the total area A. So this is EA, and cos 60 is 1 by 2. So flux phi in this case can be said as EA by 2. Okay, so now we are in the position to understand the Gauss law, because we now know how to calculate the flux. So Gauss law. Let's take an example. So like this is the positive charge inside the sphere, and this is positive charge inside it, and electric field lines due to this positive charge can be demonstrated like this. So electric field E is equals to kq upon r square r cap. Electric field due to this charge can be written like this, and k is 1 upon 4 pi epsilon naught, and here epsilon naught is the permittivity of free space. So flux phi is equals to written as E vector dot dA vector. In this case also electric field is constant at the surface, because the distance between them is same, r square is same, q is here same for each and everything, so r square is same. So and this is on the closed path, so closed is here, and electric field can be written like q upon 4 pi r, capital R square at distance capital R into r cap, and dA vector is along dA, this is dA vector is along also r cap, so r cap into dA. dA is and this is constant. This is 4 pi epsilon naught r square, and this is constant, so it will come outside the electric field. So outside the integration, 4 pi epsilon naught r square integration dA. This is cos 0. Cos 0 is 1, so this will be 1. So q upon 4 pi r square into dA vector is 4 pi r square, surface area of the sphere, 4 pi r square, 4 pi r square. So flux phi is equals to q upon epsilon naught. So flux phi we got is q upon epsilon naught. This is the famous Gauss law, and which states that flux passing through the closed surface is given by 1 upon epsilon times of charge q. So this is Gauss law, and this flux phi can be positive, can be negative, and can be 0. The positive flux means the net charge inside the sphere is positive and electric field lines are passing through this surface. And flux phi negative means the net electric charge inside the closed surface is negative and the field lines are coming inside the surface. This is like this. And the flux phi 0 means total charge inside the sphere is 0, like positive and negative, or there is no charge in the sphere, so no field lines. Or it can be said that like electric field going inside is equals to going outside, so flux phi is equals to 0. So this is the case for the flux, and we understood the Gauss law also, but Gauss law is only valid for symmetric cases. In case of symmetry, this symmetry can be spherical, and planar. Spherical symmetry means, let's take the first one, spherical. Assume like this is the positive charge q, sphere having positive charge q, and this is sphere of radius r1. We want to calculate the electric field inside this sphere of capital R radius. Take a point like this, and we can construct a spherical symmetrical case inside this sphere. So flux phi is equals to E vector dot dA is equals to summation q over epsilon naught. So charge inside this sphere of radius r1 is equals to 0. So flux phi is equals to 0. So electric field inside at r1 is equals to 0. So there is no electric field line inside the sphere of radius r1. Let's calculate another thing at radius r2. What is the electric field at radius r2? Assume this is symmetrical one. So this is r, and this is phi E vector dot dA vector and is equals to summation q over epsilon naught. Summation q is charge inside this sphere of radius r2. So this is charge q, and so this is charge q, and this is q over epsilon naught. Electric field is constant, so electric field can be put outside, and dA is 4 pi r2 square. 4 pi r2 square. So integration is gone. So this is E is equals to q over 4 pi epsilon naught r2 square r cap. So this is the electric field at point r2. So this is the case of spherically symmetrical case. So let's talk about cylindrical symmetry. Assume that this is the wire having charge density on it lambda, line charge density lambda, and we want to find out the electric field outside this wire. So this is R1, we can say. To find out this, let's assume the cylindrical symmetry, which contains like this. So this is the cylinder of radius r1, and electric field lines are like this. Let's take another color. Electric field lines are like this and going outside this cylinder, and flux phi is equals to E vector dot dA vector is equals to q over epsilon naught, and q in this case can be written as lambda into L. Charge density is lambda and the length it is covering is capital L, and radius is r1. So this is epsilon naught. Electric field is constant because distance is same, r1 here. So electric field will come outside the integration. So this is dA, closed area dA. Okay, closed area dA. dA is this one, this, and this one. So let's divide this area into three cases, like 1, 2, and this, like this type of thing is 3. So electric field is like in this direction for 1, and dA vector is in this direction, so this is dA vector. So angle between them is theta is equals to 90 degree. So E dot dA will be 0. Cos 90 is 0. Same for the second one. dA is in this direction and electric field is in this direction. So this will be flux phi. For this case it will be 0. So only third cases remains, and for third case, like this, for third case area is 2 pi r into L, surface area. So this is lambda L or epsilon naught. L get cancel out. So electric field we get is equals to lambda over 2 pi r epsilon naught r cap. So this is the electric field due to the line charge density. A wire carrying a line charge density lambda. Let's discuss the another case of planar symmetry. this is a plane having charge density sigma, and this is infinite plane, so sigma can be said as q by a, and this is infinite. So let's consider a Gaussian surface, like this is cylinder, and this will be like this going outside this. So electric field lines from this planar sheet will be like this in this direction, E vector, and for below this will be like this. And according to the previous case, this area can be considered into like three things: A1, the upper one, this is A2, and this is A3. But in this case, A1 and A3 will contribute because of electric field lines are in this direction, and electric area vector will be in this direction, and theta will be 90 for the case A2. So flux phi contribution will be 0. So flux phi is equals to E dot dA is equals to Q over epsilon naught closed. So EA plus area vector in this direction, sorry, electric field in this direction and area vector in this direction, so both are in the same direction, so theta will be 0 and cos theta will be 1. So EA, and similar for this case, electric field in this direction and area vector in this direction, so this will be EA, this is Q over epsilon naught, this is 2EA is equals to Q over epsilon naught, this will be E, and Q by epsilon naught 2A, so Q by 2A is sigma over 2 epsilon naught. This is the electric field due to the planar sheet. Assume this is small q. Alright.